Welcome to today's network seminar. Today our speaker is Dr. Vijayalakshmi Chetlapalli. So Dr. Vijayalakshmi received her PhD from the Symbiosis International University in 2020. Earlier, she did her MTech from IIT Madras and BTech from JNTU Hyderabad. Between 98 and 2000, she worked in the Department of Electrical Engineering in IIT Madras, and between 2000 and 2010, she worked in various companies. Later, from 2010 to 2019, she was a faculty member at International Institute of Information Technology, Pune, and Symbiosis Institute of Technology Management. We welcome Dr. Vijayalakshmi to give her talk. Dr. Vijayalakshmi,
thank you.
Can carry on.
Thanks. Thank you. Thanks, Krishna, for the introduction. A very good afternoon to all. Thank you for taking out time to attend this research talk. I'm Vijayalakshmi Chetlapalli. In today's talk, I'll be discussing key performance challenges that 5G access networks will face in the light of new use cases that these networks are promised to support. The aim is to present an analytical approach adopted from the field of stochastic point processes suited to model and analyze the performance challenges. I'll start with a brief summary of my work, and then I'll proceed to discuss the key main content of the presentation today. We'll look at the stochastic point process approach that holds promise in addressing modeling complexity involved in 5G networks. And then I'll also present a simulation methodology and results from simulation using MATLAB and Simulink for two types of traffic, the mobile broadband and IoT, which are two pillars of the 5G networks. And more importantly, the proposed approaches have a very wide application in addressing a lot of performance issues in 5G as well as future networks. So I'll present an overview of where these techniques can be applied in future. A brief summary. From 95 to 2002, I was with the Tenet Group IIT Madras as a research scholar and as a senior project officer, and later on I worked with an incubation company of IIT Madras. All through the 7-year period, my work was mostly centered around the RF side of the codec wireless loop network. So I studied the interference radio, mostly different effects of radio interference on the capacity of the wireless system. I also worked on a lot on propagation modeling and coverage planning for the codec installations. Later on, for the next 8 years, I have been with the Sasken and Tech Mahindra. There, my work was mainly on GPRS and Edge protocol stack maintenance for analog devices, soft phone chipset series. And I was the program manager for Pan-India mobile network testing for Vodafone, Reliance, and Airtel networks. During that period, I have also worked with the Center of Excellence in Wireless Technology at IIT Madras on ITU's LTE ratification project. From 2010, I have been in academics, and most recently, my research has been in stochastic modeling of network traffic, which was also the content of my PhD thesis. So I'm associated with most of the research that I'm going to talk about has been mentored by Dr. K.S.S. Iyer. He has guided most of my PhD work, and he's one of the founding members of the stochastic point process techniques that I will be discussing today. So he was a faculty with IIT Madras in the Department of Mathematics, and later on he retired as the head of the Operations Research Department at the College of Military Engineering, Pune. Dr. Himanshu has been my PhD guide. He is currently with the Cisco Intent-Based Networking Lab at Curtin University. I continue working with him on some IoT and edge computing problems in IoT networks. I'm also associated with Dr. Mark Gregory, who is known to Dr. Himanshu. So we all work together on a few of the latest networking challenges. Here are a few publications that are based on the work that I will be presenting today. The latest presentation that we have given was at the IEEE 5G World Forum in September 2020 on performance analysis, more or less the contents that I will be presenting today. And in April this year, we have been invited to present at, as part of the IEEE 5G tutorial series. So coming to the crux of the today's presentation, wireless access networks performance has always been a challenge, and this challenge has two dimensions. The first is the spatial dimension, where one is interested in studying the coverage, interference, and handovers of that are present in the system. The second perspective is the temporal perspective, where the queues of packets that are that pose traffic to the base station compete for resources and scheduling mechanisms. So resource allocation, scheduling, and latency involved in the packet queues is the second perspective from which the wireless network performance can be addressed. In both these cases, usually when one is attempting to understand the or model the performance from a mathematical perspective, it is assumed that both the users and the session arrivals at the base station are homogeneously Poisson distributed in space and time. However, in reality, the users or devices are present in clusters around the coverage area of the base station. Similarly, the arrivals of packet sessions at the base station change during the course of the day, and even the servicing also might change with day depending on the load offered to the base station. So this dichotomy of between mathematical modeling and the reality poses challenges for 5G networks. There are three pillars for envisaged for 5G networks. The first one is the enhanced mobile broadband, where all the broadband services that are used by humans, which are labeled as human type communications. And this second is the massive machine type communications, where the device density is estimated to be more than 1 million devices per square kilometer. And the third pillar is the ultra reliable low latency communications, where the latency is of critical issue, like in applications like self-driven cars and robotic surgeries. Here the delay is supposed to be less than 1 millisecond. Now the challenge in these applications is that the mobile broadband applications have very distinct daily traffic intensity variations as shown here. This representation is taken from an ITU report based on network measurements. Here we can see clearly that the traffic varies very distinctively with along the duration of the day for different applications. Similarly, the traffic posed by IoT applications is very sporadic in nature, resulting in very high peaks during certain intervals of the day. Now, if the 5G networks have to deliver the promise of high speed and high device density that they promise, it is very pertinent that we understand the traffic behavior with respect to time very clearly of most of the applications, so that we can come up with efficient traffic management and traffic engineering mechanisms to ensure high quality of service on these networks. So let us pose the problem mathematically. We'll start with what we know from queuing theory. So the base station is basically a pool of servers. A server would represent one or multiple physical resource blocks. So a set of physical resource blocks that can service a packet session request is considered as one server. So the packet sessions arrive at the base station at a certain rate, lambda j. We'll denote the packet sessions as service requests. Now, each of these service requests will take certain time for the base station to process, and the service requests relieve the base station at a rate or complete their service at a rate μj. Typically, in queuing theory, it is assumed that the arrival of these service requests is homogeneously Poisson distributed. That is, the lambda arrival rate lambda is independent of time. So all the quality of service parameters are functions of the arrival rate and the servicing rate. What we are interested in knowing usually at the base station is how many servers are busy, so that the base station occupancy and the number of available free resources is known for maintaining acceptable quality of service. For an MM1 queue, what we know from queuing theory is the number of arrivals in any interval 0t is simply lambda times t, and the number of departures is servicing rate multiplied by the time interval. And the number of busy servers at the base station at any point of time is the ratio lambda by mu. Now, if we observe closely, the number of busy servers here in this case is independent of time. So it is more or less an average quantity that is independent of time. This is also called as the offered load, and it is one of the principal parameters that is used in the evaluation of other QoS parameters like blocking probability and waiting time, etc. However, that model is not applicable to current day networks, mainly because the arrival rate, as we have seen, is changes during the course of the day. So when lambda changes with time, we call it non-homogeneous Poisson process. And what happens when lambda changes with time is all the quality of service parameters now become functions of time instead of being independent of time. And the parameters that we have just listed earlier are now random variables because lambda varies with time. So instead of being deterministic quantities. And since 5G networks offer a variety of services, some of which are very latency sensitive, we are also interested in answering some additional questions like how many of these service requests have been delayed by more than critical threshold, say XC. So apart from these random variables, each of whenever there is a packet session that arrives at the base station, each of the packet session triggers a random process. Say, for example, energy consumption at the base station. And this process lasts as long as the packet session lasts. And more often, we are interested in evaluating the cumulative effect of all these processes. Say, for example, if we are interested in knowing the total energy consumption by the base station in a given time interval, it will be the cumulative effect of all these random processes. Now, evaluating the cumulative effect of these processes is not very straightforward because all of these are random processes that change with time. And the aggregate of these processes is not dependent on just this particular instant where we are looking the system. It is dependent on the entire built up during the duration from the time of arrival of the packet session. So these are called non-Markovian aggregates. Such aggregates are difficult to evaluate using the using queuing theory principles. So what we are essentially looking at is a queuing problem. However, because lambda is dependent on time, we cannot use the queuing theory principles and simply extend them for analysis. So we need some new techniques to address these problems. Say, for example, the graph on the left hand side of the screen shows the traffic profile at the base station over the duration of a single day. So over 24 hours. The x-axis shows the time and y-axis is the intensity of traffic. Let us say we are interested in understanding the base station occupancy during the period from 9 a.m. to say 12 noon. And we approximate this to a linear arrival rate. One of the common extensions of queuing theory for the time dependent case is the point-wise stationary approximation for the offered load. So in the case of in case when lambda was constant, the offered load was given by lambda by mu. So it was proposed by Linda and Colliser in this reference that the pointwise stationary approximation can give the offered load for the time dependent case. Let us plot this quantity and see if this is accurate. The green line shows the offered load as evaluated using the PSA, whereas the blue line shows the result of simulation of the system for this time interval with a linear arrival rate. So what we can see is that the PSA estimate is not reflecting the behavior of the system closely. If we look at another example of a periodic arrival rate, even in this case, PSA estimate is unable to capture the simulation result. So clearly, for the time dependent case, we cannot take the offered load as simply this ratio, and we'll need special techniques to address that. There is, so what we have spoken so far is the randomness in the traffic arrival rate during the time of the, as for the time of the day. There is another level of randomness associated with the packet sessions. The packet sessions are not constant bitrate sessions. Usually, typically, there are bursts of packets that happen, and it is an on-off process. And the durations of these on and off periods have been tabulated by 3GPP and IEEE standards. So each of the applications has very specific on and off period distributions. Now these on-off periods are alternating renewal processes. So we need a modeling mechanism which can address the randomness that is introduced by time of day variation in traffic, as well as the randomness introduced during the on-off behavior of the packet sessions. I'll just skip this literature review. Only important to mention here is that we are interested in stochastic methods to address the problem. So there are two classes of techniques that address this. One is the stochastic calculus method. In this presentation, we will pick up stochastic point process methods to solve the time-dependent traffic intensity problem. So I'll proceed on to the presenting the stochastic point process model for the traffic, and see and demonstrate how we can evaluate the time-dependent performance measures.
A quick question, I would like to clarify something. Could you go back to
Sure.
the PSA approximation? Little bit behind, yeah. So in this, what you would like to ensure is that the workload is like the one on the left, and you try two things. One is the increasing arrival rate, and the other one is a periodic arrival rate. But why not try something which is a little bit like the shape on the left? Is there some constraint on lambda?
No. In fact, in my simulations, I will show a polynomial arrival rate. This is just for an example. So the actual simulations that we have carried out is for something like this.
Okay.
So I will show that in the simulation results.
You need to take into account a delay also, because you can see the periodic the response on the workload.
Yeah, right. Exactly. The response of the workload is delayed, and the PSA estimate cannot capture that delay. So what I will show is the methods that we propose will actually capture the whatever is happening on the ground very closely.
Okay. Thank you.
Yeah. Thanks for the question. That is a very relevant question. Yeah, I'll just skip the notation for now, because I'll take on the notation as the presentation progresses. This model, we look at the system as a sequence of events that happen instead of as a queuing system. So the events are arrivals of packet sessions and departures. So the entire when you are observing at the base station will see a sequence of arrivals and departures of packet sessions. So we assume that the base station is empty at the initial time. And the arrival process, as mentioned earlier, is a non-homogeneous Poisson process, so that the number of probability of n arrivals is Poisson distributed. For the current discussion, we will not consider multiple arrivals. However, the proposed techniques can be used to address multiple arrivals also, which I'll talk about in future slides. The servicing process can be generally distributed with mean 1 by mu. And to capture the time evolution of the performance parameters, we'll assume a CBR traffic. I'll also deal with on-off traffic, but at a little later stage. Now, let us first understand the complexity on why queuing theory is unable to capture this and why we need special tools to address problems where the arrival intensity changes with time. Let's say we are observing the packet sessions that are arriving at random instants of time, and at t we want to know what is happening at this system. Let us consider dividing this interval 0 to t into discrete intervals tau 1, tau 2, tau 3, and represent the number of arrivals in each of these intervals as nu I. And let x of t denote any random variable associated with the arrival events. That is, let us say we are just simply counting the arrivals. So x of I would represent the number of arrivals that are in the interval tau I. Now, if this tau space or time space is discrete, then x of t will be is a discrete random variable, and t also will be discrete, and we can define probability frequency function for x of t. However, we know that in real time t is a continuous parameter, so we cannot proceed with probability frequency function of x of t, and we cannot find the expected value of x of t. So we need to introduce special correlation functions called product densities. Simply put, a product density is a special correlation function, and it is a probability measure that represents the probability that there is exactly one occurrence of the random variable. And if we want to obtain the expected value of the random variable, we simply integrate the probability measure over the time interval of interest. Now, this will become more and more clear as we progress in formulating product density for the various random variables that we are interested in. A few notes on the product density before we proceed. As mentioned earlier, it is a probability measure. It is not stochastic intensity, or it is not probability density, as those who are familiar with stochastic modeling are familiar with these two, but product density is something different from these two quantities. In this current presentation, I will be dealing only with the expected value of the random variable, that is the first moment of random variables, but higher order product densities can also be defined, and we can also evaluate higher moments like standard deviation variance and third order statistics. The product densities have been very successfully applied earlier to several applications. As I mentioned in the beginning of the talk, these are techniques that have been adopted from stochastic point process applications in pure mathematics. So these have been initially devised for nuclear particle physics, and later on applied very successfully to other areas, but they have not been applied to communication systems so far. So what I'll be presenting today is the application of these concepts to network traffic. So the first task in so our goal is to evaluate expected value of these quantities, the number of or the offered load in the system, or number of entities that are delayed, or number of departures, and so on and so forth. These are the 4 examples that I have taken for the current talk, but there can be several such measures that we are interested in. So how we formulate product density follows these steps. First, we need to identify which random variable we want to evaluate, and then we divide we consider a very small interval of time in between 0 and t, and divide this time scale into two sections. The first one is the small interval of time d tau, and the second interval is from tau to t. And we analyze all the events that happen in these two time intervals, and then we formulate a joint probability of these events, which results in the expected value of this random variable. Now, what are the events that are possible in these two times is either there can be arrivals, departures, or nothing could be happening. So let us first start with the simplest of the random variables that we have identified, which is the counting the number of arrivals, A of t. So as mentioned earlier, we consider a small interval d tau in where tau is any time less than t, and dA of tau represents the number of arrivals in d tau. This is the common notation used in product density literature. PDA equal to 1 comma tau represents the probability that there is exactly one arrival in this small interval of time. The probability that there are more than one arrivals is represented by dA equal to n, where n can be any integer greater than 1. So we define the probability of a single arrival in this d tau to be proportional to d tau. This is very natural assumption, and the proportionality function is g1 of tau, and notice that this is a function of tau. Because we are dealing with arrival intensities that are functions of time, the probability that there is a single arrival will be also a function of time. Now, if we can recall, in the case of homogeneous Poisson processes, the probability of a single arrival in d tau is simply lambda d tau. This we know from the principles of point processes when studying queuing theory. In that case, lambda is a constant, but here g1 of tau is a function of time. This quantity g1 of tau is called the product density of first order. Now, the probability that there are more than one arrival is of the order of higher order of d tau, which d tau being very small interval, higher orders will be very close to 0, so they can be neglected. So what essentially we are saying is that we are assuming that the probability that there is more than one arrival in this small interval of time is 0. This in some particular case scenarios, this may not be true. Like, say, for example, when we are talking about massive machine type communications, where there is a huge millions of devices trying to access the base station, there could be multiple devices accessing the base station in this small interval of time. In such cases, we have to use multiple product densities, but I will not be discussing multiple product densities in the current presentation. They can be found in one of the references listed towards the end of the presentation. So the expected value of dA of tau for this small interval is the probability that there is one arrival and the summation of the probability that there is more than one arrival. And this quantity we have just seen that it is close to 0. So the expected value of dA of tau is simply g1 of tau d tau. Now, since the arrival process is non-homogeneous Poisson, g1 of tau is simply lambda of tau. So the first order product density is simply lambda of tau, because we are purely counting the number of arrivals. If we are counting something else other than arrivals, then this quantity will change, which we will see for the rest of the random variables. So now, since we have dA of tau, we can integrate dA of tau over 0 to t and obtain the expected value of the number of arrivals. So what we have essentially done here is we have devised a technique or a stepwise technique where we can come up with product density for a random variable. So the number of arrivals in 0 to t can be 0 to t lambda of tau data, which also agrees with the Poisson distribution for the time dependent arrival case. Let us now
just a quick interruption. There is a question that has been posed in the chat box. If you could answer that.
Sure. Yeah.
The question is, this looks like a continuous time Markov chains formulation, as in perhaps some Carlin's stochastic processes book.
Yes. Yeah.
Is there something that is not yet described? Could you explain?
Yeah. Usually, the time dependent queues with time dependent arrival intensities are modeled as continuous time Markov chains. That is a very common method that is adopted. This is that is why you will see some of the results matching exactly with the continuous time Markov chain results, but that may not be true for all the random variables that we will be addressing. Like say for example, when we are trying to evaluate the number of devices exceeding a certain critical threshold delay, that that might have a different approach in continuous time Markov chain. But yeah, certainly since these two, the continuous time Markov chain as well as the stochastic point process techniques, the aim is to address the same problem of analyzing the system under time dependent arrival rates. Some of the results will be very similar or even matching exactly. But
so I understand correctly, what you're saying is that there are time inhomogeneous Markov processes, but your process is more general. It need not necessarily be Markov, although to the first order, it matches the intensity of a time inhomogeneous. Thanks.
Yes, exactly. Yeah, exactly. Yes. Yeah.
Thank you. Thanks, Rajesh. Actually, I'll have a question I'll ask towards the end. Just a question on the mathematical part. I have a general philosophical question which I will.
Sure.
Which I would ask.
Yeah. Sure. Yeah. Oh, so can I proceed now?
Please go forward.
Yeah. Yeah. So we'll now try to evaluate the expected value of the most important performance measure, which is the offered load, N of T. This is the basis of several other performance parameters like blocking probability and expected waiting time and several other parameters. So this is a very critical performance measure. Now let us introduce into the notation of N tau also. We'll drop this tau a little later towards the end of the derivation. But for now, let N of tau comma T denote the number of service requests arriving at any time tau that is less than T, and they will continue being serviced at T. That is what we are trying to see is at T, we want to know how many of the arrivals that have come before T have not completed and left. So which are still continuing service. So as in the earlier case, we'll represent by Dn the number of service requests that that arrive at in this interval d-tau and continue till T. So in this case, the probability that there is exactly one active service request here, we represent by f1 of tau comma T d-tau. Notice that this is a different quantity than the previous product density. So the product density is very specific to the random variable of interest. So this is the product density for N of tau comma T, and we can also notice that it is a function of tau as well as T, unless in the previous case where it was only a function of tau. Now, so there are two events that we are interested in here. The first event is that there should be an arrival that should happen in d-tau, and the second event is that this arrival should not complete before T. If it has to be observable at T, it should continue service beyond T. It can complete service beyond T, but we are not interested what happens beyond T. We are interested in what happens at T. So there are two probabilities involved here. And we have the joint probability. If we assume that this arrival and the continuation of service are independent of each other, then we can simply take a product of these two probabilities. And what we know is the probability of arrival is lambda of tau d tau as seen from the previous slide. And this particular quantity, that the servicing time is greater than t minus tau, it represents the survival function of the servicing time distribution. Let us denote this by S of t minus tau. So S of t minus tau is the survival function of the servicing time distribution. So so now we are arriving at the expression for the first order product density of n of t. So again, like in the previous case, we simply integrate to arrive at the number of active service requests. We can simply integrate this quantity from 0 to t, and we can drop the tau here because the resulting quantity will be only a function of time. So, so we will use this expression and see if we can, if we have addressed the earlier problem of the linear arrival rate that we have considered. So the graph below depicts the estimate of the offered load obtained from product density in the red line. And here we are assuming that the servicing time is exponentially distributed. And even in the simulation, we have used exponentially distributed servicing time. Here we can clearly see that the product density can track the build-up of the offered load with respect to time very accurately. And even in the case of the periodic arrival rate, the red line represents the product density result, and we can see that it matches with the simulation result. And this simulation result is just from a single iteration, but when we average over multiple iterations, there will be a very close match between the PD and the simulation result. The number of departures can simply be obtained by using the negation of the service time of the survival function. So here we want the since we are counting departures, we want the packet session to complete before t. So this is the probability of completion. It is simply 1 minus the survival function. Now we move on to the next critical parameter of interest, which is the number of entities. Like say, for example, when we are talking about URLLC applications, where we are interested in counting the number of IoT devices which have exceeded a critical delay threshold. So in that case, we are interested in counting the number of active service requests that have exceeded a delay threshold. Now let n depend, in this case, let n xt represent the number of requests with delay less than x. We will see how to evaluate delay more than x at t. Okay. Now, the one observation that we need to make in arriving at the product density for this quantity is this represents a scenario very similar to the offered load scenario, except that if the service request has spent a time x in the system, it must have arrived at t minus x. So if we make cognizance of this fact, then what happens is instead of tau, here we had tau and tau plus d tau earlier. So instead of tau, we can replace it by t minus x, and instead of d tau, we'll have dx. So we can, to obtain the number of active requests that have exceeded a certain delay, we can integrate it from xc to t. And if we are interested in evaluating the number of requests that have completed service, that is, which have a sojourn time greater than xc, we need to multiply this quantity by the probability of completion and integrate it. So far we have discussed about the evolution of the offered load and other quantities with time of day, where T is represents the time of day variation of the traffic. In the earlier part of the presentation, we have also discussed about the micro level randomness, where the packet sessions occur as on-off process. So to address the on-off process, we can also use product densities to evaluate the number of on periods in any given interval 0, capital T. Here I will be just, yeah.
So now you're not looking at a Poisson process. So you're looking at a superposition of several on-off sources.
Exactly. Yeah. So I'll not be talking about superposition of the on-off processes, but I will just show how to, for a single on-off process, I will show how to evaluate the number of, see what we will be interested in is how many number of on periods have occurred in any given time interval 0T. Now the scale of this time period is very less. It is of the order of a few seconds, because the on-off processes traffic models are defined over the order of a few seconds. So, and the time scale that we have discussed earlier is over the duration of a day. So that will be in minutes or hours. Whereas in this case, we are talking about a smaller time scale of a few seconds over which the traffic model is defined. Now I'll just take I'll take the example of VoIP, where the on and off periods are both exponentially distributed, and the number of on periods, the product density for the number of on periods is given by this quantity. I will not delve into the details of derivation of this quantity. They can be found in this reference. And now we can evaluate the expected number of on periods in a given time interval by integrating this quantity. So essentially, product densities help us to evaluate both macro and micro level traffic intensities. So this is a summary of the analytical results that we have obtained so far. One interesting thing is with if we know the number of expected offered load or the number of active packet sessions, we can also evaluate the bandwidth for the CBR traffic by multiplying it with the rate Bj, where Bj represents the bit rate of that particular traffic type. I will now present the simulation and methodology and results. So the methodology progresses like this. First, we need to parameterize, choose which traffic type we want to model, and parameterize lambda and mu. If we have network data, this can be parameterized using machine learning techniques. But however, when there is no network, when there is no real-time data available, lambda and mu can be characterized from traffic reports that are published by various agencies like ITU or 3GPP. Parallelly, we can build, we can decide which kind of server model at the base station we want to implement. That depends on what kind of study we want to carry out, whether it is latency based study, in which case the number of servers will be restricted, or if it is just an offered load study, then the number of servers will be infinite number of servers. Now, once we formulated the product density, this has to be numerically evaluated. I have used MATLAB scripts, but then any kind of scientific computing software like Scilab or R programming or whatever can be used. So once the Simulink models of the system, now by the way, the way in which we verify the analytical result is by building a queuing system in Simulink. So the queuing Simulink offers a very flexible tools to build queuing systems, time-dependent queuing systems. So we have chosen Simulink. Once the analytical and simulation results are available, we can validate them And if there is any discrepancy, we can go back and check whether the formulation, usually what can go wrong is the formulation of the product density. If all the events which contribute to the probability of occurrence of the random variable are not taken care of, then we might find a discrepancy here. So this is an iterative process. So until we were able to match the analytical and simulation results, we need to probably go back and correct the product density formulation. So once the product densities are formulated, we can go ahead and analyze a lot of mixed traffic scenarios, and we need not bother about simulation again, because some of the heavy-tailed traffic simulations take a very long time to converge. So the advantage of using product densities is we can predict the traffic of even heavy-tailed servicing time distributions without depending on simulations which are time consuming and computationally intensive. So once the product density is formulated, we can go ahead and study those traffic scenarios. So I'll show a brief video of the simulation. So here we have, are you able to hear the audio of the simulation?
No.
No. Yeah. Okay. So the there was a question earlier. We have considered a time-dependent polynomial arrival rate here, and the server we will be evaluating the offward load here. So the server is infinite server. I have used exponential distribution in this simulation, but we can use any kind of even heavy tail distribution like hyper exponential or Pareto or whatever, whichever is suitable for that particular type of traffic. So this is streaming video traffic arrival rate distribution. And what we can do is we can capture all the quantities at the server or the base station. Well, the number of active sessions, the number of completed sessions, as well as server utilization. So the arrival rate function here is a polynomial arrival rate. The time duration of the simulation is for 24 hours. That is, the traffic arrival rate is defined over 24 hours. So all the output parameters can be captured in this sink and then be processed graphically later on. Let us now run the simulation and see. The MATLAB scripts can control the execution of the simulation, so we can change the servicing rate, or we can change the arrival rate parameters using MATLAB scripts, so that we can run multiple iterations in one go. So we'll run the simulation and see and observe how the results of this polynomial arrival rate will be. Yeah, so the simulation results are plotted here. This represents the arrival rate. This is the inter-arrival time. And this is the expected value of number of arrivals. This is the expected A of t. This is expected D of t. What is of interest for us is the number of active packet sessions, that is, which is the offered load. We can see that the number of active sessions varies stochastically with time. This is from a single simulation. So we can run several such simulations and average the results over this 24-hour period, so that this smooths out. Okay, so taking that simulation model, we have simulated two types of mobile broadband applications, voice and streaming video. the servicing time distribution for voice is assumed to be exponential, whereas for streaming video is known to have heavy-tailed servicing time. That is, the number of long video sessions is considerable. So we have simulated hyper-exponential servicing time distribution as well as exponential. So we will compare these two cases and see how the offered traffic varies across these two servicing time distributions. Since we will be evaluating offered load, the queue is an infinite server queue. These are the results for voice traffic. The x-axis represents the time of the day, and y-axis represents the offered load or number of sessions in service. We can see that the results from product density follow very closely with the simulation results. The green line represents the arrival rate function, which varies polynomially during the duration of the day. So there are two clear distinct peaks, one at 11 a.m. and one at late in the evening at around 9 p.m. The graph on the right hand side represents the number of completed calls. Here also the product density is able to estimate the quantities very accurately. What I'm not showing is the error analysis of these simulation results because because of the paucity of time. However, we have calculated the scatter index and root mean square errors for all these simulations, and we have found that they are within agreeable limits. The 3D graph below shows the bandwidth, that is the number of active sessions multiplied by the bandwidth per packet session, and we can see that both the simulation and the product density results match. This is same type of same quantities now are represented here for the video sessions. One of the key observations that we have to see for the video sessions is that if we look at the case where the sessions of the video, the length of the video sessions is varied from 1 minute to about 2 hours, because we took 2 hours so that it will represent the sessions that are full-length movies or sporting events. Now, when the video session length is high, like say for this blue line, the peak of the offered traffic lags the peak of the arrival rate by a certain amount, a considerable amount of time. So for example, the peak of the arrival rate happens at around 9 p.m., whereas the peak of the offered traffic happens at around 10 p.m. So this lag is captured perfectly by the product density. This slide shows the effect of heavy tail distribution on the streaming video traffic. Let us take this case of this purple line, where the we can see clearly that the solid line represents the offered load for the exponentially distributed service time, whereas the other three represent the offered load when the servicing time is hyper exponentially distributed. Here we have varied the probability P with 3 different values. What this simply represents is, let us take the dashed line, hyper exponential, with 10 minutes duration, 10 minutes video length duration. This represents that 93% of the video sessions have 10 minutes duration, and the rest 7% are of 150-minute duration. So what we can see is that the heavy tail traffic results in much higher offered load, and this increase in offered load magnifies as the duration of the video session increases. And as mentioned earlier, the delay or the lag in the offered load also increases with the length of the video. And what the below plots show the bandwidth requirement for in the case of hyper exponential and exponentially distributed video session lengths. What we can see is that for hyper exponentially distributed video session lengths, the bandwidth requirement is about 100 Mbps higher than the bandwidth requirement for the exponentially distributed video sessions. So, and this is again very clearly captured by the product density. We'll move on to the next type of traffic, which is the IoT traffic. The behavior of IoT traffic is the way we analyze IoT traffic is slightly different from the HTC traffic. In the case of IoT traffic, we have considered two different applications. One is the smart metering applications, where a large number of smart meters send periodic updates to the nearest base station. Whereas smart alarm applications are applications which send data to the base station upon the occurrence of a particular event. Like say, for example, seismic sensors, whenever there is an earthquake or vibration in the Earth's geology, they send data to the base station. There is a marked difference in behavior of these two types of traffic, which we will show in the next slide. In this case, in the case of IoT devices, the devices are large in number, so they contend for the radio resources at the base station. But the data that they have to transfer is typically very small. So most of the engagement that they have with the base station is in the contention resolution. So most of the time is taken up by the random access procedure, whereas the data transmission procedure might be just a few packets of transmission. So we consider the entire random access as well as the data transmission time as the servicing time. Now these are the traffic types proposed by 3GPP for the two types of smart metering and alarm traffic. The smart metering traffic is assumed to be homogeneous Poisson process, because this will be uniformly distributed in time. So this is just the total number of devices divided by the randomization period. Now, all the quantities here are defined by 3GPP traffic model. Whereas the type 2 alarm traffic is beta distributed. That is, there is a very the traffic rises very fastly, and then it also goes down slowly. The randomization period for the type 2 traffic is just 10 seconds. Here in this case, we are interested, apart from the offered load, we are interested in estimating the number of delayed devices. So we present the simulation results for two types of mechanisms, the infinite server and the single server cases.
Dr. Vijayalakshmi, just a small notice. So the time is 5 p.m. now. So
right. Yeah, I'll try to finish as quickly as possible. So this slide shows the offered load characteristics of the smart metering and the alarm traffic. As we can see that the alarm traffic rises quite fast, and it is defined by the beta distribution. The graphs on the above row show the variation of increasing total number of devices on the offered traffic. Quite naturally, as the total number of devices increases, the offered load also increases. But what is interesting to see is that the effect of, let us say each device takes 150 milliseconds to complete the access and the data transfer part. Now, if this servicing time is increased from 150 to about 1000 milliseconds gradually, what we can see is that the offered load also increases. So, and the peak of the offered load also again shifts by a couple of seconds. This is a phenomenon that we have observed in the streaming video traffic also. And in this case, again, product density model captures this drift in the peak offered load. So this is a parameter that we haven't listed so far. The number of devices exceeding a delay threshold X is plotted here. for the Poisson case and the beta distribution case. Now what we can see is that again in estimating this quantity, product density does really well in capturing the number of delayed devices. I would like to mention here that these simulations are carried out for the single server case because we are interested in delay analysis. I'll skip the mixed traffic scenario except for that the third case where here we have plotted the combination of MTC and HTC traffic, that is the IoT as well as the mobile broadband traffic, and we can see that the IoT traffic, when the number of devices is very high, results in very high peaks whenever it occurs, and these peaks can hamper the quality of service of the HTC services. So such kind of analysis can be carried out with using product density. So finally, the applications of product density are not just limited to understanding the temporal variations of traffic. We are also working on the spatial traffic analysis, where the arrival rate depends on both the position of the user as well as the time instant. So we can define product densities in both space and time and estimate several space-dependent QoS parameters. Another interesting application is ITU has proposed a machine learning framework for traffic engineering for 5G networks and the future generations of networks. Here, what they propose is that the traffic streams be clearly identified and classified as per the behavior of several parameters. So it becomes very practical to integrate traffic prediction algorithms into these machine learning orchestration framework, where the QoS parameters can be predicted using product densities. The third application comes from Cloud RAN and edge networks, where edge computing networks in both Cloud RAN and edge computing scenarios, the access mechanisms and backup algorithms and scheduling algorithms play a very critical role, because there will be because these are pooled server systems, the amount of traffic is really high, and product densities can be used to examine the performance of these systems. The final application comes from the necessity to evaluate the energy consumption at the base stations. Now, this has been a very critical performance concern in 5G networks, and it will be so in future networks also. As mentioned earlier, we can evaluate the aggregate of such continuous time random processes using what is called as random point process technique. This has not been discussed in the current discussion, but it will be very useful. This in turn uses product density for evaluating the moments of these aggregate processes. So we can evaluate energy parameters using product densities and random point process together. And we can similarly do energy profiling of the IoT devices. So this brings us to the what I have to present. I'll be happy to take any questions.
Yeah, thank you. Yeah, the floor is open for questions. So if you have any questions, now the time to ask.
Dr. Vijayalakshmi, Nidhin here.
Yeah.
Your service time models, they were all like exponential models, right? Or any general model. How do you take into account the queuing delays? You have a finite bandwidth. Maybe I didn't understand the model fully, but you have a finite bandwidth available at any given point in time. So you only have a finite number of servers available.
Sure.
So is that taken into account in the model? So somehow I did not get that point.
Yeah, very good question and very pertinent. We have in the results on delay, we have taken a single server model where there is a resource constraint, right? So the results for the delay part, where we have estimated the number of the devices that have exceeded a certain delay, that is a single server model. Similarly, we can evaluate the performance measures for k number of servers. What your question, I understand, is instead of infinite servers, can we do the same for finite number of servers? Yes, definitely we can do that. Yeah, and we can also do it for different any kind of generic servicing time distribution. Remember that when we were evaluating offered load, one of the right hand side parameters in the product density evaluation was the survival function of the servicing time, right? So that survival function will now depend on k number of servers instead of infinite number of servers, and then we can certainly evaluate the offered load in that case.
Yeah, so the survival function will then be a function of the n also, right?
Yes,
the current
exactly.
load.
Yes, yeah. So, indirectly it will be, indirectly it will be a function of what you say, restricted number of servers, let's say k servers. And we are also actually working on the case. I understand that where you're coming from. What you are mentioning is that the rate of servicing at the base station could also change with time, depending on the number of existing number of sessions. Exactly.
Yes.
Yeah. So we are actually currently working on that problem. That is slightly involved because mu of t in that case is one thing, a function of time. Secondly, it is a function of n of t itself, right?
Correct.
So
Yes,
it is in some way inversely proportional to n of t. So we are currently working on that problem, and and I think probably in a few months' time we will have results for that.
Okay, thanks.
I had another question, somewhat related to what Nitin asked about. So when you talk about the video conferencing applications or even streaming video, typically there is a feedback effect involved, where there is, like, depending on your service rate, actually the arrival rate changes. So how do you incorporate feedback in this kind of setup? Something similar to the queuing networks, what they do provide.
Yeah, exactly. So what we can do is this is, I think what you are saying is essentially captured by Nitin's question. That most of the streaming video applications now are variable bitrate applications. So the bitrate is varied according to the actual number of sessions already going on in the system, right? So again, the same question, the same answer I have is that we have to change mu as a function of time instead of having a deterministic, a time independent mean. We will have a time dependent mean for the servicing time distribution.
As far as I understand, mu will also reflect your latency, right? Here, in principle, your lambda is changing rather than mu.
Lambda is changing. See, in the current results that I have shown, we have kept mu independent of time, or it is independent of the offered load. So mu is a separate distribution in itself, right? But we can have a feedback loop where it depends on the n of t, or in turn it depends directly on lambda of t. So as lambda of t increases, we would like the servicing or the pooled number of servers to be increased or decreased accordingly, right? So that analysis is still under study for us. We are evaluating product densities for that, And I'm sure the results will be very interesting because this reflects a very real world scenario.
Okay, thank you.
Yeah, yeah.
Okay. So if there are no more questions, then
Yeah.
let's thank Dr. Vijayalakshmi for her talk.
Yeah.
Thank you.